All right. In this first lecture, we're going to do a bit of a review. So I'm not going to spend a whole lot of time on the individual slides, but I just want you to have a picture of some of the topics that I kind of want to refresh your mind with, so that they will, because we'll use them later in some of the other topics. So I want to sort of talk about atomic structure in this first module. So let's go ahead and look at that. All right. So the very basics here, when we're talking about atoms, right? You should recall from a lot of other classes, but you should recall that the nucleus here in the center is composed of protons and neutrons. This one is carbon, so it has 6 and 6. The number of neutrons can change for the various isotopes, but the number of protons is the same. That's the atomic number. And then it's orbited by the various electrons. And here, this is known as a Bohr model of an atom. And so you see them at very discrete radii from the nucleus. And so that's something that we will discuss. All right, so speaking of those electrons, again, Bohr model here, very specific radii. And so in general, what this tells us, and the conclusion we reach, is that an electron's energy, and therefore its orbit, so its position here around the nucleus, is what we call quantized, right? It's at discrete levels instead of just anywhere. And so that's something that we're going to look at. And that quantized nature brings up the 4 quantum numbers. So hopefully you've seen these before. I'm not going to go into an extreme amount of detail here, but the principal quantum number, which the symbol is usually n in most resources, and those are integers starting in 1, going up to infinity, and these define the shell, right? So if we go back to this, these are the K, L, M, N. These are symbols for 1, 2, 3, 4 in values. So the shell, the distance away from the nucleus, is generally defined by this principal quantum number. The next one, which goes, a lot of these you might see slightly different names or slightly different symbols, but the second one here is the angular momentum. I think Zumnal in some references, but this is the second quantum number, usually L, and it goes from 0 and then integers up to n minus 1. So if you have n equal 1, you can have values of only 0, right? Because it only goes up to n minus 1. 2, you can have 0 and 1, and etc. So these are our subshells. So this kind of defines our subshells. And we'll talk about what this gives us. Next, we have the magnetic quantum number. M sub L is usually what it goes by, but these are defined by the values of L. So you can see here it goes from minus L through integers to 0, and then the same thing to positive L. So again, using the reference here, if we only have n equal 1, that would be L equals 0 is the only option, and so we just have 0, whereas if we have 1, 2, which would give us 0 possibilities of 0 and 1, the 1 would give us minus 1, 0, 1, and if we had 2, that would be minus 2, minus 1, 0, 1, 2, etc. Right? So these define the various orbitals. And then the last one is the spin quantum number, m sub s here. Again, different references, you might see different symbols, but m sub s for us. And this basically defines that there are 2 electrons per orbital defined in the magnetic spin number. And so we put these spin states as plus 1/2 and minus 1/2. So we have 2 electrons for each of these various orbitals, and all this together kind of gives us the orbit of the electron, its energy defined by these quantum numbers. So if we're looking at a given element and we want to know kind of the filling order of how the various orbitals are filled, we can use this schematic. So I won't spend a lot of time on this. This is something that's covered in MSE 201, but the idea is if you have something like copper with an atomic number, you know how many electrons there are, and if you want to know where those electrons are located in the various orbitals, you can use this schematic. And it'll work majority of the time. There are some exceptions, copper actually being one of them, but you'll get very close to the correct order. But essentially the numbers 1, 2, 3, those define the principal quantum number n, and then the lowercase letters S, P, D, and F, those define the L values, and then within those you get the number of electrons based on how many orbitals there are, defined by the magnetic and the spin quantum numbers. So an S will have 2, P will have 6, D will have 10, and F will have 14. And if that seems, if that is new to you, make sure you go back and kind of review the quantum numbers and the filling of electrons. And the last thing I'll kind of mention here in this kind of review on atomic structure is the Schrodinger wave equation. So this is something that's usually covered more in a quantum mechanics class, but the basic idea here with what I want to leave you from this, and we won't necessarily do too much with this because it's a second order derivative, and there's a lot that goes into solving this. But the main takeaway I want you to have from this is that the old adage that you've heard about electrons is that their position and momentum can't be known exactly. Both of those cannot be known, right? And the Schrodinger wave equation kind of is the solution to this, in that we're looking at probabilities. So instead of being able to know exactly position and momentum, the best we can hope for is a probability of where the electron is located. And that will lead us into the next module, talking about the orbital shapes for electrons.